We have a few limits here to evaluate in example 3, and it looks like I'm just kind of looking at those values here. We've got either infinity or negative infinity to evaluate. So let's take a look and see what happens with the end behavior of these things here. And so if we take a look at that, that's really just the horizontal asymptote as well. If we take a look at this numerator, it has x to the first power, and there's an x squared down here. If we wanted to, we could add a filler, 0x squared in the top to make those two agree. So you have to have, when you're trying to find the horizontal asymptote, you have to have the exact same exponent in the numerator and denominator, or at least degree. So you should look for the highest one that you see. And the highest one here in the bottom is x squared. We need to put a 0x squared in the top. These guys will cancel out, and we'll be left with 0 over 1, which is 0. So the limit as x approaches infinity, which is the same thing as end behavior or the horizontal asymptote, is just 0. If you looked at a graph of this, this rational equation, each side, as a matter of fact, both infinity and negative infinity, the value of y that each end of the graph would approach would be 0. With this one on the right-hand side, we're trying to evaluate this for negative infinity. We've got 2x plus 3 over 3x plus 1, and already I'm seeing an x here and an x here. So if we were to try to find a horizontal asymptote, we would just look at that highest power, make sure the numerator and denominator agree, cancel those out, and we've got 2/3. It's really as simple as that with most of these. A and B worked out pretty well. C and D, though, that might be a little interesting. And this one, I don't have any good way to find a horizontal asymptote other than to look at shifts. So if you look at this shift right here, this is a shift up by 2, and we have the same function here in C and D. So the normal regular old horizontal asymptote for y is equal to 2 to the x, or y is equal to 3 to the x, or y is equal to e to the x, or e to the negative x, that is y is equal to 0. So for each one of these functions, there's a horizontal asymptote at y is equal to 2. We need to be very careful with these exponentials, though. If you remember the shape of these things, the shape of them, they look kind of like, well, I'll draw it here for you. They look sort of like this. This one is going to be reflected over the y-axis, so it's actually going to look something a little bit like this. So maybe we can cross that one off. And here would be your axes right there. And it's also shifted up too. The left-hand side, though, the value of y approaches infinity. The right-hand side approaches that value of the asymptote. Let's take a look at the graph of this just to make sure we haven't made a mistake. And so I'll type in caret, let's see here, we'll go negative x, close that up, and then do and add 2. And we'll wait for the calculator to do something. Here we go, and it looks like that graph is leveling out at a y value of 2. So if we're investigating the limit as x approaches infinity, if we go to that table that we had before, and we go, let's see, to the right, towards infinity, you can see that that value is basically 2. And we can write that here for our answer. As a matter of fact, we could say yes, indeed, this is 2 as x approaches infinity. As x approaches infinity, it gets very big. This is e to the negative whatever power, really big power, 100 or negative 200 or negative 300, and that's just going to be 1 over e to the 200 or 300 power or whatever it is, which is close to 0. So this whole part of the equation, as x gets big, is just getting close to 0, but then we have to add 2 every time, and so that's why the limit here is 2. This one, though, is a little bit different. So this one, we could say either one of two things, depends on what your teacher wants. For me, it doesn't bother me either way. I kind of like to see you state the positive or negative value of infinity that it goes to. But some folks would say that this limit does not exist because as we go to the left towards infinity, this graph climbs and climbs and climbs, but we'll note that it climbs to positive infinity. So if you'd like to write this down for a function similar to this case, then go ahead and do that. But just keep in mind, some folks would write does not exist here because infinity is not really a value. And if a function continues to infinity, well, it's continuing without limit or limitless.